Good morning, students. I welcome you all for the another session. Today we're going to see two problems. Okay, that is how to find out the UDL on the beam. Okay, the first problem is like this: a singly reinforced concrete beam section 230 mm into 550 mm is reinforced with 4 bars of 25 mm diameter with an effective cover of 40 mm. The beam is simply supported over a span of 5 meter. Find the safe UDL the beam can carry. So use M20 grade concrete and Fe 415 steel. So as usual, we are going to draw the cross section. This is width of the beam. So B is given 230 mm. Then here it is a overall depth. Okay, not mentioned any effective depth. So capital D is 550 mm. Then effective cover is given. See, this is the effective cover. So from center of beam, center of steel to the bottom is effective cover. So effective cover will be 40 mm. So the total depth is 550 mm. So 550 total depth minus this effective cover 40. So we'll give the effective depth. Say that is 510 mm will be the effective depth of the beam. So that is from top to center of reinforcement. Then FCK, that is characteristic compressive strength, 20 Newton per mm square, because grade of concrete is 20. Then grade of steel is 415. So Fy is equal to 415 Newton per mm square. Then area of steel, so it is given 4 bars. Okay, 4 bars of 25 mm diameter. So 4 into 5 by 4 diameter square. Okay, so we'll give area 1963.5 mm square. Okay, so this will be the total area of steel for this 4 bars. Now as usual, effective span will be given 5 meter. So the effective length of the beam will be 5 meter. Now as usual, first step will be, we will going to calculate the actual depth of neutral axis, that is XU. Okay, so as you know, XU by D is equal to 0.87 Fy AST divided by 0.36 FCK B into D. Okay, so substitute all the values. 0.87 Fy 415 AST 1963.5 divided by 0.36 FCK is 20, B is 230, and effective depth small d is equal to 510. So we'll get XU by D is equal to 0.84. That is actual neutral axis depth XU by D is equal to 0.84. Okay, so even you can calculate XU is equal to D into 0.84. Okay, so this is first step. Next step is we're going to find out limiting depth of neutral axis or maximum depth of neutral axis, that is XU limit or XU max, and this depends on grade of steel. Now which grade of steel is used? Fe 415 grade steel. So for Fe 415 grade steel, directly you can note down XU max upon D is equal to 0.48. Okay, for Fe 415 grade steel, XU max upon D is equal to 0.48. Now compare these two values. Okay, XU by D and XU max upon D. So comparing XU by D with XU max upon D. So what you can observe here? So XU by D is greater than XU max upon D. Okay, so what it indicates? So if XU by D is greater than XU max upon D, the beam section is over reinforced section. Okay, the beam is over reinforced section, then it will be restricted to limiting condition now. Okay, now we're going to find out next step, ultimate moment of resistance, MU limit. So it is over reinforced means we're going to find out MU limit. So ultimate moment of resistance, MR, it is MU limit. Again, this MU limit for over reinforced section, it depends upon the grade of steel. Okay, so for Fe 415 grade steel, MU limit is equal to what? 0.138 FCK BD square. Okay, 0.138 FCK is 20, B is 230 mm, and effective depth 510 square. So this comes out to be 165.11 into 10 raised to 6 Newton mm. Okay, force into distance. So Newton mm. So divided by 10 to the power of 6, we will get mu limit is equal to 165.11 in terms of kilonewton meter. Kilonewton meter. If you multiply 10 to the power of 6, it is Newton millimeter. Okay. Now this is the ultimate moment of resistance, mu limit. Now what was asked in the problem? So you have to find out what is the total UDL that can be taken by the beam. Okay. Now this is ultimate moment. Okay. Ultimate moment. This we are going to divide by 1.5. So we'll get working moment of resistance. This is ultimate moment of resistance, mu limit. Now we'll calculate working moment of resistance, this mu limit divided by 1.5. So we'll get m. So instead of mu, now it is m. M means working moment, mu means ultimate moment. So m working moment is equal to, we'll get 110.07 kilonewton meter. So this divided by 1.5, it is 110.07 kilonewton meter. This is working moment. Okay. Now see, this is a beam, simply supported beam. This beam is simply supported on these two supports. Then span will be 5 meter. And this is the UDL. So this UDL is because of its self weight. Okay. The self weight of the beam will be acting in the form of UDL, that is small w per meter. Small w per meter. Okay. Now, what is the maximum bending moment for this condition? Simply supported beam subjected to UDL throughout the span. The maximum bending moment at the center will be WL square by 8. Okay. So this is for simply supported beam subjected to UDL, maximum bending moment will be WL square by 8. Now there are two moments. This is moment of resistance, this m, small m. This is the resistance given by the beam against the maximum bending moment. The bending moment will be coming how much? WL square by 8. So to resist this will be the moment of resistance. So now equate these two. Okay, equate m is equal to m max. So that is m max is equal to working moment of resistance m. So this is W L square by 8, that is equal to m 110.07, equating these two moments. So here only the unknown is W. So W into span L 5 square divided by 8 is equal to 110.07. So W is equal to 110.07 into 8 divided by 5 square. So we'll get 35.22 kilonewton meter. So this is the total UDL. I am writing total UDL, means it includes live load plus self weight of the beam. Live load as well as self weight of the beam, the total load will be 35.22 kilonewton. If I want only the live load, okay, if I want only live load, then what we are going to do? This total load minus self weight. So live load is equal to what? Total load minus self weight. Then we are going to get UDL in the form of live load. But here this total load W, that is UDL, this UDL includes self weight plus live load. So this was the quantity they have asked. So the total UDL will be 35.22 kilonewton per meter. This is UDL means kilonewton per meter. So this is one problem. Now let us take another problem. Okay, the problem is like this. A rectangular beam section 250 mm wide and 500 mm deep up to the center of tensile reinforcement consists of 4 numbers of 22 mm diameter bars. Find the position of neutral axis and safe moment of resistance, that is MR, if concrete is M20 grade and steel is Fe415 grade. So along with this, they have asked find what concentrated load, that is what point load or concentrated load it can carry at mid-span. So along with UDL, right, how much point load will be there at the mid-span of the beam if the beam has an effective span of 6 meter. Okay, again draw the cross section, width of the beam, and here beam width is given 250 mm and this 500 mm. See, 500 mm deep up to the center of tensile reinforcement. So this small d they have given 500 mm is the depth of the beam from top to the center of reinforcement, means it is effective depth. Okay, small d is equal to 500 mm. Then area of steel, so 4 bars of 22 mm diameter, 4 bars of 22 mm diameter given, so we can calculate the area will be 1520.53 mm square. Then FCK, characteristic compressive strength, 20 Newton per mm square, and Fy 415 Newton per mm square. Then effective span L is equal to 6 meter. So effective span will be 6 meter. So as usual, the first step will be calculate the neutral axis XU, that is using this formula XU by D is equal to 0.87 Fy EST divided by 0.36 FCK B into D. Substitute all the values. Okay, so find out XU by D first, then XU is equal to D into this value. XU is equal to what? XU is equal to D comes this side, D into this whole term. So XU will going to get 305 mm, or even you can calculate this directly XU by D also. So XU is equal to 305 mm. Now next is second step is limiting depth of neutral axis, that is XU max or XU limit. Okay, so XU max for Fe415 grade steel, XU max is by D is equal to how much? 0.48. Okay, XU max upon D is equal to 0.48. So therefore XU is equal to D into 0.48. XU max is equal to D into 0.48. So it comes out XU max is equal to 240 mm. Okay, XU max, that is limiting depth of neutral axis, 240 mm. Okay, depth. So now right now we have two depths, XU, that is actual neutral axis depth, and XU max, that is limiting depth of neutral axis. Compare these two. Okay, compare these two. So since this XU is greater than XU max, see this is 305, XU max is 240. So XU is greater than XU max, so the section is over reinforced section. So this first step remains same. Okay, so since XU is greater than XU max, the section is over reinforced section. Now it is, if it is over reinforced section, then we are going to calculate MU limit, or if it is under reinforced, then we will calculate MU only. Okay, if it is over reinforced, it is MU limit. So for Fe415 grade steel, MU limit is equal to 0.138 FCK BD square. Okay, so therefore MU limit is equal to, substitute the values, find out MU limit. So this is 172.50 into 10 to the power of 6 Newton mm, or divided by 10 to the power of 6, we will get 172.50 kilonewton meter. So convert this Newton mm to kilonewton. Newton to kilonewton divided by 10 to the power of 3, then millimeter to meter again divided by 10 to the power of 3, means totally we have to divide this by 10 to the power of 6. So this 10 to the power of 6, denominator 10 to the power of 6 cancels, we remains 172.50 kilonewton meter. This is ultimate moment of resistance MU limit. Now divide this by 1.5. Divide this by 1.5. What we are going to get? Working moment of resistance, that is M. So M is equal to MU limit divided by 1.5. So we'll get this 115 kilonewton meter. This is M. Working moment of resistance. Resistance given by the beam will be how much? 115 kilonewton meter. Now what they have asked? Find concentrated load at mid-span. Now see here. Again this is the simply supported beam. Simple support at A and simple support at B. for a span of 6 meter. Effective span will be 6 meter. So there is a UDL, that is small w. Okay, this is due to live load plus self weight. Okay, this will be acting in the form of UDL. So along with this, there is a point load, concentrated load. They have asked what concentrated load at midspan. So concentrated load or point load at midspan, I will write this as capital W. So remember, small w means it is a UDL, then capital W means it is a point load at the center. Now we have to find out what is this point load W, what is the value of W. Now again, simply supported beam, now there are two loads now. One is, this is UDL in the form of, that is due to self weight and live load, and this is concentrated load, point load. Now what is the maximum bending moment for this condition now? So without this point load, if you don't consider point load, then it is simply supported with UDL. What is the bending moment, maximum bending moment? Small WL square by 8. Okay. Now without this UDL, simply supported beam, only point load at the center. What is maximum bending moment? It is capital WL by 4. This is simply supported beam with point load at the center, only point load at the center, maximum bending moment is WL by 4. And this is simply supported beam with UDL, okay, WL square by 8. So maximum bending moment for this condition, because there are two loads, this is maximum bending moment due to UDL, this UDL, and this is maximum bending moment due to only point load. Okay, Mmax is equal to WL square by 8 plus WL by 4. So where this small w is what? UDL due to self weight. Okay, UDL due to self weight, and capital W is a point load, that is concentrated load or point load. Okay. Now, so we are first we are going to calculate the self weight of the beam. So for self weight of the beam, we have to calculate capital D, that is overall depth of the beam. So overall depth of the beam, that is capital D, we have to calculate, but capital D is not given. Small d we know 500 mm, that is from this to center 500 mm, and we can assume this effective cover. Okay, assume this effective cover from center of this steel bar to the bottom. This is called effective cover. So this small d plus effective cover will give the capital D, overall depth of the beam. So now, assuming effective cover 40 to 50 mm, okay, you can assume this 50 mm. Therefore overall depth of the beam, capital D, is equal to effective depth, that is small d plus effective cover. So we will get 500 plus 50, 550 mm, this is capital D. So now what is self weight of the beam? Self weight of the beam is cross sectional area of the beam, B into capital D, width of beam into overall depth of the beam, capital D, into, it is made up of what? RCC, we have to multiply density of RCC. So area of the beam, okay, total area of the beam into density of RCC. So B, now because this is 25 kilonewton per meter cube, density of RCC will be 25 kilonewton per meter cube. So this is in meter, means this B and D also substituted in meter only. 250 mm means 0.250 meter. 0.250 meter B, capital D 0.55, that is 550 mm. No, 550 mm meter means it is 0.55 meter into 25 kilonewton per meter cube, density of RCC. So we'll get small w, that is self weight of the beam in the form of this UDL, is how much? 3.44 kilonewton per meter. Okay, 3.44 kilonewton per meter. So therefore, now there equate working moment, this maximum M maximum, okay, maximum bending moment equated to moment of resistance. M is equal to this M max. Okay, equating working moment M, this moment of resistance M equated to maximum bending moment, that is M max. So M is equal to what is maximum bending moment? This WL square by 8 plus capital WL by 4. WL square by 8 plus WL by 4. So M is this working moment of resistance 115 kilonewton meter. Okay, that is equal to WL square by 8. W, small w, we have calculated just now 3.44 kilonewton. So 3.44 L square, span is 6 square divided by 8 plus capital W we have to calculate, that is point load we have to calculate, keep as it is capital W, into L is again 6 meter divided by 4. So this comes out how much? 15.48, this is 15.48 plus 6 by 4 means 1.5 capital W. So this 115 is equal to 15.48 plus 1.5 W. So what we want? We want capital W, that is concentrated load or point load. W is equal to 115, this term goes this time, 115 minus 15.48, okay, that is 1.5 W is equal to 115 minus 15.48. So therefore capital W is equal to 115 minus 15.48 divided by this 1.5. So you will get concentrated load capital W is equal to 66.34 kilonewton. Okay. So along with this UDL, that is sulfate UDL 3.44 kilonewton, this is UDL. Along with this UDL, there is a point load of how much? 66.34 kilonewton at the center of the beam. So this was the problem. So please note that this is the important problem for your exam point of view. Okay. So today we have solved two problems. So once again I request you all solve these two problems. Okay. And in the next session, in the next class, we are going to start with type 2 problems. Okay. So whatever the problems we have solved here, okay, all these are type 1 problems where we will going to find out the moment of resistance, okay, M or MU, okay, or we are going to calculate the loads, okay, that is type 1 problems. In type 2 problems, moment will be given directly, moment will be given, we are going to calculate the area of steel now. Those are type 2 problems. Okay. So whatever the problems till now we have solved 5 problems. Okay. So solve all these 5 problems once again, and if you have any doubt, okay, feel free to ask me. Okay. So thank you very much for attending this session, and hope I will solve some more problems, type 2 problems in the next session. Thank you very much.